Hi, all you sake lovers out there. It's time for another episode of Sake Science, the series that all the cool sake nerds are watching. In my last video, we looked at how amino acids contribute to the taste of sake, but there's another important way in which they influence the sensory profile of sake, and one which is slightly less appreciated. So this time, let's take a look at how amino acids affect sake's aroma. Before we get into it, I have a question for you. Without using Google or a reference book, how many aromatic compounds in sake can you think of that are derived from amino acids? I'll give you a bit to think, or you can pause the video. Okay, so did you come up with anything? Well, here's a chart I compiled from the aromatic compounds measured in the National Research Institute of Brewing's 100-year aged sake project. They actually measured many more compounds than shown here, but I limited it to those that had odor activity values of close to or over 1, which indicates a significant contribution to the aroma. Thus, these are the compounds every sake professional should be able to recognize. Out of these 15 compounds, 11 are directly derived from amino acids or their metabolites. So, how many were you able to think of a few minutes ago? Don't feel bad if you couldn't think of many, because this is really a big issue in sake education, where the origin of the sensory elements of sake is really treated as kind of a black box, leading to misconceptions such as overemphasizing analogies between rice varieties and grape varieties used for wine, for example. I'll be talking about most of these underlined compounds from the chart in this video and the next one, and my hope is that this will give you a somewhat more accurate sense of how sake's aromatic properties come about. Out of all the compounds that come from amino acids, those known as the higher alcohols, fusel oil or fusel alcohols, are the most important for a number of reasons, both good and bad. Yeast converts branched chain and aromatic amino acids to fusel alcohols by what's known as the Ehrlich pathway. In the process, the yeast gets nitrogen to form glutamate, which is a central compound from which other amino acids are synthesized. In this process, yeast also creates NADH, which is a cofactor used in other metabolic processes and energy-producing pathways. Sake contains a few different fusel alcohols, but two are most important from a sensory perspective. Isoamyl alcohol, which comes from leucine, and phenethyl alcohol, which comes from phenylalanine. Isoamyl alcohol can be somewhat fruit-like at low concentrations, but in higher amounts it can resemble magic marker or even rubbing alcohol. If you've ever run across a sake that smelled harsh and solvent-like, it was probably due to too much of this. Phenethyl alcohol, on the other hand, is a component of the aroma of roses, and thus can lend a floral note to sake. As we can see from their respective odor activity values, they make similar contributions to the aroma of sake, even though phenethyl alcohol is present in smaller amounts. This is due to its lower threshold compared to isoamyl alcohol. Of these two fusel alcohols, phenethyl alcohol seems like something we might want to have more of, and in fact researchers have developed yeasts that produce much larger amounts of it, as well as its honey-like ester, phenethyl acetate. Here's an example using Kyokai number 9 yeast and its high phenethyl alcohol producing mutant. And we can see the latter produces almost 10 times the amount of intensity of phenethyl alcohol. However, despite these yeasts having seemingly good fermentation power and other characteristics, it's hard to find products that are actually advertising using any of them. This might be because consumers actually don't want a sake that smells like perfume. Another reason might be that some of these mutant yeasts also produce more of other aromatic alcohols like tyrosol and tryptophan, which, along with phenethyl alcohol, have been found to contribute unpleasant acidic, bitter, and astringent tastes to sake, even in low concentrations. Although isoamyl alcohol might likewise seem undesirable on its own, it's actually indispensable for the production of the banana or pear-like aromatic ester isoamyl acetate, which is one of the main components of the prized ginjo. You see, after leucine is transformed into isoamyl alcohol by the Ehrlich pathway, it can further be changed by yeast into the acetate ester by an alcohol acyltransferase enzyme known as ATF1P. So it would seem if we wanted more fruity ester, we could give yeast more leucine, right? In theory and in practice, this works. If we just give yeast directly more pure leucine, it will produce more isoamyl alcohol and more isoamyl acetate. But in brewing, the most straightforward way to increase the amount of leucine available to yeast is to use rice with a higher polished rice percentage. But this introduces a problem. Less polished rice also provides more unsaturated fatty acids, which block the formation of ATF1P, and also more of the sugar inositol, which blocks its function. Thus, we can end up with much more of the harsh isoamyl alcohol, and this is in fact one of the reasons behind using highly polished rice for ginjo zukuri sake. But what if there were another way to get to isoamyl alcohol without raising the polished rice percentage? Well, it turns out there is. Yeast actually has the ability to synthesize its own amino acids from pyruvate derived from glucose. And in the case of leucine, it's a multi-stage process that goes through isoamyl alcohol. However, this process requires energy, so use of pyruvate in pathways to create energy, such as fermentation, is favored. Thus, when there's sufficient leucine around, it blocks the function of one of the enzymes needed for amino acid synthesis. But can we release that brake somehow? In fact, it's been done by isolating yeast that are resistant to the toxic leucine analog trifluoroleucine. Here's an example of the effect that has. Here we have the odor activity values of isoamyl acetate and the alcohol in sake made with Kyokai number 7 yeast and one of its trifluoroleucine resistant strains. We can see the acetate and alcohol both increase in intensity, but if you do the math, you'll see that the ratio of ester to alcohol remains almost exactly the same. We don't really want a sake that smells like a banana-scented magic marker, so what we really would like to do is increase that ester to alcohol ratio. This can be done by developing yeast with increased expression of that acyltransferase enzyme that produces the ester. But this enzyme is not very selective, and it will esterify other alcohols such as ethanol, leading to more ethyl acetate, which smells like nail polish remover. So is there another more selective way to get more isoamyl acetate? By chance, there is another alcohol acyltransferase enzyme called ATF2P that normally doesn't have much effect on isoamyl alcohol, but again, by isolating yeast that are resistant to the toxic steroid precursor pregnenolone, which is esterified by this second enzyme, we can increase its expression. And here's an example of the results. This is actually with laboratory S. cerevisiae and not sake-specific strains, but it gives us an idea of the effect. We can see that overexpression of ATF1P produces a huge amount of isoamyl acetate relative to the alcohol, but also large amounts of ethyl acetate, which is considered a definite fault at this amount. Overexpression of ATF2P doesn't yield nearly as much isoamyl acetate, but the ester-alcohol ratio is still greatly improved, and we're not getting quite as much ethyl acetate in the bargain. Now, I didn't go through all the details of isoamyl acetate production by yeast just because I'm a big nerd, but to highlight the fact that development of desirable characteristics in yeast exploits, modifies, or repurposes naturally occurring metabolic pathways which have been shaped by evolution and thus are subject to natural selection. Yeast don't want to make fusel alcohols or their esters. They're minor byproducts in the process of catabolizing or synthesizing amino acids. But selection has led to their production having some benefits to the yeast. As for fusel alcohols, they're important signaling molecules for what's known as quorum sensing. This is how yeast sense how much other yeast is around, and it affects their growth and metabolism. But too much of any alcohol, including ethanol inside the cell, is toxic. So esterification helps transform the toxic alcohol to the less toxic ester, while also regenerating the crucial compound coenzyme A for other metabolic pathways. Finally, yeast that produce esters that by chance resemble ripe fruits have been shown to attract insects like fruit flies, which can then carry the yeast on its body or spores internally, helping the yeast spread and propagate. So now let's take a look at a sake that's made with one of those high isoamyl acetate producing yeasts, and this one is called Mahoroba Kagua, and it's from Aomori. And fittingly, one of the brands that uses it is Mutsu Hassen's Isaribi, and this is from Hachinohe Shuzo in Hachinohe City in Aomori. And it's pretty available overseas. This is the Hiire version. And yeah, you can get that banana isoamyl acetate aroma right off the bat. It's kind of like a banana pudding in a way. And compared to other, other sake where they really try to raise that ginjo ka with a lot more isoamyl acetate, this has a lot less of the alcohol in it. I can really tell. It's pretty rich up front. It's not necessarily sweet. This is actually a pretty dry sake. It's the driest one that Hachinohe Shuzo makes, or I think the driest one in the Hassen brand. I've seen different numbers for it from +5 to +8, and I think that varies depending on the year. And it's a lot of people mention how clean it is in the finish. Yes, it has a very, very clean finish. And this actually, even though it's hiire, it has a little bit of effervescence left in it. And a bit of bitterness in the finish, actually. Um, it's almost kind of beer-like to me. And I think it would go really well with oily foods, that bitterness and that crispness. So I'm going to try it with actually something tonight, and I'll let you know how it goes. Before we wrap things up here, I want to talk about the Maillard reactions, which are particularly important for the appearance and aroma of aged sake. If you've taken any kind of sake course, you've probably learned this name, but again, what exactly is going on might still be kind of a black box to you. I use the plural for a reason, because the Maillard reactions are a complex series of reactions between sugars or their degradation products and amino acids or their derivatives that can yield colored polymers called melanoidins, Strecker aldehydes, which we'll look at more closely in my next video, and heterocyclic aromatic compounds that provide distinctive aged aromas. A heterocycle is a ring-shaped molecule in which one of the carbons is replaced by nitrogen, sulfur, or oxygen especially. By far the most important of these in aged sake is called sotolon. This compound is detectable at just 2.3 micrograms per liter, which is thousands of times lower in concentration than most of the other aromatic compounds in sake. Depending on its concentration and one's cultural background, it can resemble maple syrup, or burnt caramel, or even curry powder. Despite the fact that sotolone contributes to the aroma of things like aged rum and wine like port, as well as sake, surprisingly not many details are known about its formation. But the proposed pathway one often sees is this. First, glucose or another sugar and the amino acid threonine or perhaps serine react in a number of stages to give alpha-ketobutyrate. This then reacts with acetaldehyde present to yield sotolone. So obviously higher concentrations of sugars and amino acids will promote sotolone formation, which is why we see more of it in sweeter and richer sake. But temperature is also hugely important, as we can see from this graph. I've adapted it from a study on sake aged in different conditions, and here we have the odor activity value of sotolone in sake aged at ambient temperature in green and below 15 degrees C in red. We can see clearly that warmer conditions produce much higher amounts of sotolone, but levels seem to peak after about 10 years. On the other hand, the increase in cool stored sake is much slower, reaching its threshold value of 1 only after many years of aging. However, the authors did identify some examples of cool stored sake with higher levels of sotolone, such as ones stored in whiskey barrels or tanks with more exposure to oxygen, and this is also known to contribute to sotolone formation. But this is one of the reasons why we can have cold stored ginjo zukuri sake that is still fruity and has low levels of sotolone. So it's important to remember that not all aged sake is alike. So here's an example of an aged daiginjo sake that I picked up on my trip to Joetsu last year. And this is from Yoyo Giku Jozo, and it's called Challenge Chibitagawa. They said that they had aged it for 3 years and decided that it was ready to go and were really happy with it. And if we look at it, if you can see the color there, it's just lightly colored, light little amber color. And on the nose, in this case, I'm getting a good amount of sotolone. It actually, if it reminds me of anything, it reminds me a lot of very diluted soy sauce. But I'm also getting hints of something else, some nuttiness, something like ume, or Japanese apricot, which I think is probably coming from another compound called benzaldehyde, which can be present in aged sake, and I'll kind of talk about that in the next video. But other than that, it's pretty clean. There's a little bit, there's some fruitiness left. It's kind of like, I often say this, it's kind of like cooked or poached fruit, like a poached apple or something. It's really delicious and um, like a lemony kind of acidity. I've had that only in one other aged sake, that kind of lemoniness, but also very much, I don't get a lot of caramel like this way. Like from the orthonasal aroma, I don't get a lot of caramel, but from the retronasal aroma, it's like a lot of caramel. So I hope I've given you some more insight into how amino acids can contribute to not only the taste, but also to the aroma of sake. In fact, we wouldn't have these distinctive sake aromas without them. As always, please like and subscribe and stay tuned for the last part of this series where we'll take a look at how amino acids can negatively affect sake. And until then, keep exploring sake.